Right, so time to get started. Thanks everybody for coming to the final defense of Maxwell Kimball. My group. Let me give you a brief introduction and then I would suggest we just get started. And before we start the question and answer session with the committee, I would ask you to then go step outside. So Max got his Bachelor of Science degree at Worcester State University. He worked briefly as a technician in industry for Lubbock Laboratories and joined my group in the summer semester of 2020. That was in the middle of the COVID time, but we managed very well during that time. So Max has been working on a variety of projects. Going backwards in time, the last 2 years, we had a collaboration with Albemarle. So unfortunately, he cannot tell about his results, which were very exciting, but he has plenty other things he can talk about. So one of his big projects was to obtain an immobilized Sonogashira catalyst system with immobilized palladium and copper complexes that he studied with solid-state NMR. He also had a brief collaboration with the Rossini group, where he provided copper complexes for deeper NMR analysis. And what he will mostly focus on today is also the post-polymerization studies of polymers. So he implemented the HR-MAS method that allows us to study better kind of prefabricated polymers and use the model system of LDPE. We also have to have a parallel universe of kind of academic papers because the industrial things we are not allowed to just write up and publish. That needs to be held back until the patents are done. Another project was with adducts, aluminum trichloride adducts of phosphine oxides, where he managed to get 31 phosphorus mass and 27 aluminum NMR spectra, which are something special in the solid state. And so just to finish this up, he has done his share of teaching, and he got various travel awards that he used to go, for example, to ACS meetings. And he also got recently a second place poster prize at the Polymer Technology Consortium meeting. So how does it go on? We still have 2 papers to write for the company Albemarle, and then he's going to join Lintec. So he already has his job offer signed up on that. And so that will be his future. So, okay, so I leave the stage for Max to give his presentation.
Thank you. So today I'm going to be talking about 3 projects: solid-state NMR, aluminum chloride triphenylphosphine, aluminum chloride phosphine oxide adducts, HR-MAS of LDPE, and some molecular and immobilized palladium and copper catalysts. So I'm going to start with the aluminum chloride phosphine oxide adducts. Aluminum chloride is a strong Lewis acid, so it's used in industry, for example, very commonly in Friedel-Crafts alkylation. So you can take benzene, which is a relatively low-cost material, and then alkylate that to ethyl benzene, and then reduce it with the iron catalyst to make polystyrene, which is a very valuable consumer plastic. You can also use it in halogenation reactions, for example. So if you want to make a flame retardant, you commonly just halogenate the material to make it less flammable. Phosphine oxides are also really useful synthetically and analytically. They're used to probe acidic sites of different materials. So for example, this zeolite here, you can apply in a substoichiometric amount of phosphorus and see what sites are most available. And you can also get an idea about how populous each site is and how acidic it is using phosphorus solid-state NMR. And you can also use them synthetically. So we make these hydroperoxy phosphine oxide adducts, which are stable and stoichiometric and non-aqueous oxidizers. So these hydroperoxy adducts are useful, for example, in direct esterification. So we reported on that previously, and you'll notice that the aluminum chloride is also in the direct esterification scheme. And we know that that's a stronger Lewis acid than these hydroperoxy groups. So you can see with the X-ray diffraction, the bond length of the phosphine oxide bond, the PO bond, is longer with the aluminum chloride adducts, and that's indicating that it's a stronger adduct ring. So we wanted to look into these aluminum chloride adducts and characterize them so that we could start to probe what role those play in this direct esterification reaction. We synthesized these through melting and grinding, but those give kind of amorphous materials. So all the spectra that you're going to see moving forward were synthesized in solution. So we get nice crystalline materials and good solid state NMR spectra. So solid state NMR is dominated by chemical shift anisotropy. So that's this characteristic shape here, and that's defined by these delta 1,1, 2,2, and 3,3 peaks. So if you have a material, each of these peaks will be unique to that material. But this is a very broad signal. So to reduce measurement time and increase our resolution, we use magic angle spinning. And so that's just turning the sample around at the angle of 54.7 degrees relative to the magnetic field. And that angle theta is here in the Hamiltonian of the chemical shift anisotropy. And so when we plug in 54.7, that 3 cosine square theta minus 1 term goes to 0. So that whole part of the chemical shift anisotropy is reduced. And so instead of the big broad shape, we get the isotropic peak and then discrete rotational sidebands at intervals of the rotational speed. And you can see that these sidebands kind of mimic the shape of the chemical shift anisotropy. And so we can plug in the intensity of all of these rotational sidebands and back calculate the delta 1,1, 2,2, and 3,3 values to characterize the material. So that's what I did. Starting with just the phosphine oxides, you can see that the chemical shift anisotropy is pretty wide. And the reason for that is that the chemical shift anisotropy comes from the dipole, the anisotropy around the shielding of the phosphorus nucleus, right? So if you have a big dipole from the phosphorus to the oxygen, the shielding's less symmetric, and so you'll have a larger chemical shift anisotropy. So I calculated all of the CSA parameters using DMFit. And yeah, you can see a span of about 190 ppm, and then all of the delta 1,1, 2,2, and 3,3 values there. And then as we make our adduct, the adduct is having a much reduced chemical shift anisotropy. And that's because the strong Lewis acid's pulling that oxygen back, right? And so the phosphorus is feeling less influence from the oxygen, and so that dipole is being reduced. And so because we have a smaller dipole, we have a smaller chemical shift anisotropy. Also, we see the isotropic peak is shifted up by about 28 ppm, and so that's just indicating that the phosphorus is more deshielded overall, which is what we'd expect from these. Also, we only have one isotropic peak, and so that tells us something about the crystal packing, because the isotropic peak depends on the crystal. So if you have, for example, 4 different molecules in the unit cell, you can have up to 4 peaks if you only have the one polymorph. But all of these phosphorus nuclei are in very similar environments, and so with the resolution of the spectrometer, we only see 1 peak. So we did this for a couple different phosphine oxides. We have triphenylphosphine, orthotoluene, paratoluene, and cyclohexyl. And you can see in each case, the chemical shift anisotropy is reduced and the isotropic peak is shifted up quite a bit. And so I calculated the CSA parameters for all of those. And in most cases, we see it reduces from about 200 down to about 100. And then the isotropic peak moves from kind of the 30 to 50-ish region of phosphine oxides that you would expect up to 50 to 76 ppm, which is pretty high. So next we're going to look at 27 aluminum NMR. A 27 aluminum is a quadrupolar nucleus. that means that it has a spin greater than 1/2. So if you have a spin of 3/2, then you have a satellite transition, a central transition, and a satellite transition, and those are kind of um, the characteristic peaks of the quadrupolar spectra. Aluminum is actually 5/2, so it'll look just like this, but it will have a central transition, and it should have 2 satellite transitions. Right. Quadrupolar interactions are also susceptible to magic angle spinning, so we also get discrete rotational sidebands. So we get improved resolution and shorter measurement times with those. And the strength of the quadrupolar interaction, if you're looking at the same nucleus, is going to be depending on the electric field gradient around the nucleus. So as we change to different phosphine oxides, you'll see that the size of the quadrupolar interactions will change. And that's just because of how symmetric the electronic environment around the aluminum is. So I started with just 27 aluminum NMR of aluminum trichloride. And this is a nice octahedral aluminum, so it should have a very symmetric electric field gradient. And we see the span is still almost 3,000 ppm. So it's pretty large compared to the phosphorus. And we have lots of rotational sidebands, even at 10 kilohertz of magic angle spinning. And the signals are kind of broad too. If we move on to our adducts, then you can see we get even broader. So now we're over 3,000 ppm, and it's pretty impressive. There's a lot of manual baseline correction. Spectrometer doesn't like to play nicely when your sweep width is 4,000 ppm. So these were a little bit of a work to get. But you can see that we have a central transition there, and then our first satellite transition, and then our second satellite transition is kind of over here. And if you want to characterize the quadrupolar interactions, there's some deeper analysis that we didn't really care to go into. Also, it can be kind of difficult because the satellite transitions aren't so, sharp. They're kind of broader. So we didn't look into characterizing the quadrupolar interactions more than just looking at the span. Also, the central transition shifted up by almost 90 ppm. So that was surprising. It was a lot more than I thought it would be. So the triphenylphosphine has the largest span of over 4,000 ppm. And it also has a really interesting shape, which is characteristic for quadrupolar nucleus. So a lot of quadrupolar spectra have these interesting central transition shapes that kind of look like lopsided Batman. But the rest of these have reduced spans, and they kind of have a Gaussian-Lorentzian central transition. So that's telling us these triphenylphosphines have the largest quadrupolar interactions and the least symmetric electric field gradient, right? We didn't look into analyzing this too much because it's only like 7 data points. So it's kind of limited data that we could get from that. So here's all the aluminum spectra, and you can see that there's kind of undulating waves. So that's kind of interesting. You might think, okay, there's your first satellite transition, and then your second, and then there's another peak over there. So we didn't really look into these too much, but it was kind of interesting to see. Okay, we also collected FTIR and X-ray diffraction. My coworker Raheem collected these, and all of these tell us something about the strength of the interactions. So FTIR and X-ray diffraction agree across the board, of course, because they're measuring the same thing, PO bond, right? So aluminum and phosphorus are measuring the shielding environment around the nucleus, and so there's some disagreement about like, okay, if you have the strongest adduct, then you should be pulling away density, and so you should see the bigger shift with the strongest adduct. But for example, the FTR X-ray diffraction, say that's 2, and that's 4 according to phosphorus NMR. All right, but we characterized all of them. And we know what each of them looks like, and the data is a little interesting, but we'll have to look at that in future studies. This was enough for one paper. Okay, so now we're going to talk about HR mass of LDPE with solvent soaking. So basics of NMR, your resolution depends on the length of the FID. So if you have a longer FID, and then you use a Fourier transform, so if you have a longer FID of more data points for the Fourier transform, and you can get a nicer resolved signal, right? So the length of the FID is dependent on the T2 time. So we're looking, if we want to have good resolution, we want to have kind of long T2 time, right? But polymers don't have long T2 times. They have shorter T2 times than most materials, and that's because of limited mobility. And so if you have a nice small molecule, T2 is directly related to your rotational correlation time, but we have, big long strands that get tangled up, and so most of their mobility isn't real rotational correlation. It's kind of axial rotation and wagging and things like that. So they're not going to play as nicely as nice small molecules. So they have quote unquote long rotational correlation time, and that leads to short T2 time, and that leads to a shorter FID, and that shorter FID means you have broader signals, right? So if it was a perfect world, we could just measure the half width and get the T2 time. But that's not really possible because we have that requires a perfectly homogeneous field, and we don't have that. So instead, we'll just compare the half widths, and the half widths should be, closely related. Okay, so we started with just LDPE pellets and 400 millimeter LDPE granules. We tried them both. We just ground up the pellets into nice small granules, and they didn't really make a difference. Then we soaked them in solvent for a good long while to get them nice and fully saturated. And then we packed them in this HR mass rotor with kind of the minimum solution that we can get, so that we see we have as few solvent signals as we can get. We have big signal just from the LDPE. So if we have no magic angle spinning, we get really broad signals. If we have 10 kilohertz, we get sharper signals. And then if we have HR mass, which is soaking with, in this example, chloroform, and then 2 kilohertz of rotational speed, then we get even better resolution. So HR mass is a nice technique if you want to improve the resolution of the polymers. And we applied that, like Dr. Blumel said, with other companies characterizing their polymers and seeing if we can make chemical changes and see that. So this is proton solid state NMR, which is pretty unusual. Proton has a really high gyromagnetic ratio, and so you have very strong homonuclear dipolar interactions. But we can resolve even the ethylene and the methyl peaks. So this is a good technique to use. If you just have a simple material, you want to know the degree of branching, for example, then you can make kind of a calibration curve with a particular solvent that you have. And if you already know the degree of branching, then you can quickly build a library, right? And then you could use that to characterize materials. So yeah, we can resolve both of those peaks, and we have pretty good resolution, double what we see if it's just a dry material, even with the high rotational speed. And carbon NMR will get intrinsically better resolution, right? We have a larger chemical shift range, and we have much weaker non-existent homonuclear dipolar interactions because 13 carbons pretty dilute, right? So we get better resolution, and you can see, again, even in the solid state, we have 230 hertz, which is much better than proton. And then with HR mass, we see again about a 2 times increase in the resolution. So this is kind of the best tool if you want to be characterizing interesting polymers. And you can see again the ethylene chain and then the methyl groups there. And if you want to kind of close your eyes and pretend or squint and pretend, then you can imagine these shoulders are probably the tertiary carbon branching groups. We don't know the degree of branching for this material, so we didn't investigate that at all, but there are signals of it. So we wanted to characterize these materials with the T1 times as well. So T1 is related to mobility. It's used, for example, in MRI, and it's easier for us to measure than T2s. That's what's commonly reported in the field. So, for example, in MRI, you can see the skull is a nice hard material, and that gives a shorter T1 time. And so that shows up as brighter. And then the intracranial fluid has a longer T1 time because it's a fluid, and so that shows up as darker. And then everything in between is grayscale. And you can kind of infer the mobility of that tissue. So measuring T1 is pretty straightforward. We used inversion recovery. So if you imagine this is the superposition of the nucleus, and that's kind of the axis that it's rotating on, it is usually in its relaxed state aligned with the magnetic field. And then we give it a 180-degree pulse, and then we wait some time tau. And as we're waiting, it will do T1 relaxation, which is kind of what I've drawn here, which is going back up to the relaxed state. And it will also do T2, and so that's starting to decohere the signals. Okay, so that's going to shorten our FID. So we wait some time tau, and then we do a negative 90-degree pulse. And so that flips it up. And importantly, it reverses all of the T2 relaxation. So now instead of decohering, they're starting to recohere. And so the length of the FID is only dependent on T1. So then we can just integrate all of the signals that we get and plug that into this equation here and get our T1 time. So if we wait our perfect time tau so that it relaxes 90 degrees, that's T1. That's what we're trying to calculate, right? And catching that is hard, so yeah, we'll use the math instead. So we did that for a couple different materials, and you can see all the stacked spectra here, and we plug all of that data in, and we get pretty good fits. And you can see our T1 time is in the kind of quarter second to half a second range. So as a dry material with 2 kilohertz rotational speed, we're about 0.2 seconds. And when we soak it with chloroform, which is kind of the best performing HR mass solvent, we see an increase up to about half a second. So that's showing that we have a good degree of increased mobility. We also wanted to see if that solvent penetrating into the polymer network can bring in a small molecule. So we used nicolicine as an example. So nicolicine is a catalyst. We could theoretically use that for polymer degradation. It's also strongly colored and paramagnetic. So we can visually see that it's penetrating all the way in 3 millimeters through this pellet. And we can also see because it's paramagnetic, it won't overlap in the NMR. So we can get that pretty easily. So we soaked that in. We found that we can get in about 12% of nicolicine, which is pretty good. And then we just rinsed that off really quick and took that material, dried it, and took that for NMR. And then we also re-wetted it and took that for NMR. So the dry material shows a chemical shift anisotropy. This is proton NMR, right? So it's shifted way over because it's paramagnetic. This is the nicolicine signal. And so it has a chemical shift anisotropy, but it's different from the polycrystalline material, and it has a reduced Haft width. And so what that's telling us is that it's not the same crystal packing structure, right? So it's either discrete molecules distributed throughout the LDPE, or it might be co-crystallizing with the LDPE or something like that. But it's definitely not just nicolicine crystallites embedded in the material. And we did HR mass, and so you can see that the nicolecene no longer has chemical shift anisotropy. It's just a single broad peak. And so that's telling us that it's being mobilized when there's solvent. So it is able to penetrate into the polymer network. And then when we reintroduce solvent, it's going into the solvent again. So we're kind of doing like rudimentary gel chromatography. If you have, for example, plastic that you want to recycle, this is something that you have to show. You can put in a material and take it back out. FDA has requirements on being able to show that you can pull out contaminants from a plastic if you want to use it in food or medical packaging. Also, we see the LDPE signal has an increased half width over just regular HR mass. So T1 times don't observably change for the LDPE, but the half width grows from 2.5 kilohertz to 5.5 kilohertz. And that's kind of in line with the literature that we've seen previously, or that my coworker Gabby measured actually, that nicolecene and ferrocene solid solutions will have, the ferrocene will have the same T1 time, but it will have a broader half width. So that's kind of interesting, but I guess not too unexpected. So in conclusion, I showed that HR mass gives us better resolution. It's useful for characterizing, and we can get an idea of how well that polymer is being mobilized by the solvent and how well that solvent can carry in and out analytes. And that was pretty useful for our industrial collaboration. So lastly, I'm going to talk about these molecular and immobilized palladium and copper complexes. And this is my favorite project. This is kind of the cool thing that I really wanted to do. So we're targeting making a catalyst for Sonogashira coupling. Sonogashira coupling is any aryl halide with the terminal acetylene, and then we use the palladium and copper catalyst to couple those. And this is really commonly used in pharmaceuticals, for example, very mild reaction conditions, pretty high yield, and this internal alkyne is a pretty common moiety. But pharmaceutical has a problem with palladium catalysts because the FDA requires you to have very low residual palladium and copper in the finished product. And so also they're expensive. So we want to be able to use our palladium efficiently. So that's why we're making a new catalyst. So we're targeting doing this transmetallation step here. So there's a copper cycle and a palladium cycle, and you transmetallate to get that alkyne onto the palladium so that you can just reductively eliminate that off. And this is what's commonly believed to be the rate determining step. So we want to see if we can do that faster. And so we thought, okay, if we just put the palladium and the copper on the same molecule, then we don't have to wait for them to diffuse into each other. It might be able to just do the transmetallation intramolecularly. Wouldn't that be nice? So we made this, and it doesn't really work that well because it dimerizes. If you make it in situ, it works great for a few minutes until it dimerizes. If you make it and then you put it in, it doesn't work, already dimerized. So we thought, okay, we can prevent this dimerization by just fixing the ligand onto the surface, except the ligand is not stable anymore. So that just gets hydrolyzed and you get methyl diphenylphosphine in solution, and then you have 2 phosphines where you should have 3. So we have to rethink this, and we'll just take what works and add 1 more methylene in there and try to see if that reduces the steric interactions and makes that silicon-carbon bond a little more stable. So we'll make these tripodal phosphine linkers with 2 methylenes. And these ligands show up in the literature a little bit. Interestingly, if you take a square planar metal, like a nickel 2 or palladium 2, it makes these drone type complexes. They kind of stack on top of each other. And so there's only 2 examples in the literature. This is it. So we thought, okay, well, we're already going to be making a new ligand, and might as well see if we can get a couple of these as well. So we're going to start with the solution chemistry for drones. Making the ligands is pretty straightforward. We just start with the trivinyl silane, and then add in a bunch of diphenylphosphine and do radical initiated hydrophosphonation. And then we can just vacuum distill off all of the excess diphenylphosphine, and we're left with the really viscous, thick oil. So that pained me for a long time. I couldn't figure out how to get rid of the oil until I tried diethyl ether or acetone. And for some reason, those act as a crystallization aid, and you just get big rocks of pure ligand. It's awesome. It's great. Not good enough crystals to get X-ray diffraction from, but good enough that we can get pretty good purity and pretty much quantitative yield. And then we just add in our palladium, and we get the metal complexes, right? Only one phosphorus signal because they're all equivalent. No huge surprise there. Looking at the ligand, we can do silicon and carbon NMR, and you can see some phosphorus splitting. So all of our aryl peaks in the ligand show up as doublets. And then in the silicon, we get a nice quartet because it has J coupling to each of those 3 phosphorus nuclei. We also had carbon NMR of the ligand. So this was interesting because we see triplet of the drone complex. And this is interesting because we see triplets. So we're actually seeing virtual coupling over the palladium, which is seen sometimes, but it's not so common. It's kind of noteworthy that we're seeing it. So instead of getting a doublet of doublets like you might expect, we just get triplets. Kind of neat. We also got X-ray structures for a handful of these. So we made this methylsilane, and that went so easy. It was like the second try I got big crystals, and I made like a ½ gram of them. It was great. And then I made this methoxy, and that was a lot more work. It took about a month, and then I got a crystal structure that's kind of on the edge of publishable. So, okay, we'll take it. And then this ethoxy was even harder. So I tried for, I don't know, 5 or 6 months with every solvent under the sun and vapor diffusion and solvent layering, and we never got there. Instead, it would just make amorphous blobs. And then I would set that on the counter and hope. And a month later, I would get crystals. And what happens is just water gets in and cleaves, and you make this silanol. And the silanol crystallizes, no problem, easy peasy. So we'll take that. We went into deeper analysis of all of these crystal structures in my dissertation, but I won't bore you too much with that. We'll move on to making an immobilized palladium copper bimetallic complex. This is kind of a tall order, and because it's an immobilized complex and the surface coverage of the ligand is not so good, we only really have solid state NMR as our analytical technique. XPS is too insensitive. X-ray diffraction is insensitive and gives not particularly useful data. Same with FTIR. The data is just, I mean, you can tell they're different materials, but it's difficult to get, real chemical information from it. So we just stick with solid state NMR, and we'll move kind of methodically to make sure that we have each step looking okay. So mobilizing these ligands is pretty straightforward. We just take our ligand in a toluene solution and we add it to well-dried silica. And then if you dry the silica well enough, there's really only surface silanols. And then those silanols will cleave that off. You'll hydrolyze that off and get ethanol, and then you'll have a silanol. And then that silanol will condense with the silanols on the surface. And so if we do that and then we wash off anything that's not bound, we get about 52 milligrams per gram coverage, which is not so good. Like I said, it's relatively dilute. And this is with the 750 square meters per gram silica. So relatively high surface area. The ligand's just kind of bulky and, oh well. So you can see with HR mass, when everything is really immobilized, if it's in solution, you get a sharp signal. It's like 10 hertz wide in a solid state spectrometer. And then as you wash the material, that sharp peak goes away, and you're just left with that broad peak underneath, which is your real immobilized material. So HR mass can show us that everything's actually immobilized. We don't have any surface cleavage. So we have the same shift about as in solution. So that's nice to know. We don't have any big, strong surface interactions or decomposition. Then we can make our palladium complex. And if we have 100% surface coverage and we add our palladium, we actually consume all of the phosphine. So there's no more leftover ligand signal. And the palladium should only coordinate 2 phosphines. So what that's telling us is that we're actually sharing between ligands, which kind of makes sense. If you're supposed to have 100% surface coverage, it would make sense that you have phosphines that are relatively close together. And so we consume all of those phosphines, and I think that's because we're sharing between ligands. You might note that the solution drone complex was at 21 ppm, and these surface complexes are 31 ppm. And well, why is the difference, right? We want to make sure that this is a surface interaction because that kills the catalyst. So we thought, okay, it's about a 10 ppm shift. That might match the difference between having a cis complex and a trans complex, right? If we're going to make a trans complex with this, it might be a little sterically challenging to fit that on the surface. So I devised this experiment and I checked in the literature, and the literature says, yeah, about 10 ppm. If you have the same complex, you move from cis to trans, it's about a 10 ppm change. And if we make the drone complex on the surface, then we see, yeah, okay, about a 10 ppm change. And we consume a fair bit of that, and we have that signal there. That's the same signal that we see in solution. So it seems like we don't have surface interactions. It's just a difference of cis to trans shift. So next I made the copper component just to see what that looks like. And that's pretty easy. So you just take excess copper chloride, you put it in there, makes this tetrahedral complex. And the shift is not so crazy. It only goes from -10 to -3. So pretty straightforward. So then I made a dilute coverage of this tripodal phosphine. And I was looking to make it dilute so that we can try to prevent sharing between molecules. Because if we're going to share between molecules, well, we want to try to make it so that there's 1 palladium and 1 copper per molecule, right? If you can share between, then you might have patches of palladium and patches of copper. Does that make sense? So we reduce the surface coverage and we add in our palladium, and now we see cis and trans signals. And so my thought there is that now that we have a little bit of breathing room in between each molecule, it might be more favorable to make this trans complex in some scenarios. Those phosphines kind of spread out a bit, and we have a 7-member ring there. So it's kind of more reasonable, and it can work. If you're pessimistic, you might also say that, okay, well, now it just needs to reach across a little bit farther to share between molecules. And so that instead of a cis coupling, it has to stretch and make a trans coupling. Yeah, maybe. But kind of we're at the limit of what we can measure. I thought, okay, at 31p nosy, too far to really see. So we'll just hope for the best and move on. So we took this material and we added 1 equivalent of copper, and that goes pretty much how we'd expect. It does move from a -3 or -4 to about -1. It's a different complex too. So phosphine copper complexes are all kind of not great chemical shift, and they kind of exchange a lot. And so that's within the region that they should be. So looks okay. No big metal-metal interactions that would drastically change the chemical shift. No big surface interactions that we can see. So far it looks okay. So let's just move on and see if we can do catalysis. If we're making the complex that we think we are, and it works the way we're hoping, we should see the catalysis should be significantly better than what we see in the literature. So first I fixed the GC and calibrated it and got nice curves for all of my starting materials and my product. And then I did catalysis and we turned over. It works. We got product, starting material dropped down. I was able to fit the curve and get pretty good agreement. And from that, I modeled that we should have reached equilibrium about 10 or 11 hours in. And if we look in the literature, a lot of other catalysts will achieve pretty much stoichiometric conversion within about 6 hours. So not a ground-breaking catalyst, but this is also, I've run this twice with the same material. So it could just need more tinkering to really work. But so far it seems like, I don't know, a little iffy. But we got catalysis going, and it seems like it's working, at least as a catalyst. So that was nice and reassuring. And so with this project, I found, okay, we have a tripodal linker. It makes metal complexes. I know what all those look like. We can make solution complexes, added a few more complexes to the literature, filled that gap. Only 2 of those. Now there's 5. That's kind of cool. And we got a pretty good understanding of how these materials work, I think. So that was that project. And that brings me to the end of my defense. Thank you for Rahim for co-authoring the aluminum trichloride adduct paper, and for my coworker John, who helped with the HR Mass LDPE paper. He's no longer with us. He's at L'Oreal in New Jersey now, but thank you, Rahim. Any questions?
Great talk, by the way. Really well done. You go to 31. To the super great one.
Sure.
Might be a bit of a silly question, but I don't think you ever mentioned what that is.
Oh yeah, that's the broadband, the background signal from the probe.
Ah,
Yeah, so the rotor and the probe have Kel-F, which is like a fluorinated polymer. But there's residual, there's carbon in it, right? So that's what that is.
okay.
Yeah, just the background signal. Thanks. Any other questions?
That's not the case, and the audience has to leave now. He's going to run